In our last video, we learned how to convert some basic quadratics into the vertex form. However, the examples we looked at only had a leading coefficient of 1, and all the parameters in our final answers were integers. So, how does this process work when we have a different leading coefficient? And what will the process look like when we start working with parameters that aren't integers? These are the questions that we'll address in this video as we continue learning how to convert into the vertex form. The first issue that we're going to address is when we have quadratics with a leading coefficient other than 1. What this means for the vertex form is that we have to start including a value for a. And while this might seem like it will complicate matters quite a bit, we've actually already built up the necessary tools for dealing with this situation. Consider this example. If you think back to our work with leading coefficients while converting to the factored form, our first step there was to check for a greatest common factor, which is essentially going to be our first step here as well. However, there's an immediate problem, which is that the greatest common factor here is just 1. And factoring out a 1 won't change anything about the expression. When it comes to the vertex form, though, it turns out that what we really care about is factoring out the leading coefficient, regardless of whether or not it goes into each term evenly. So in this case, we want to rewrite the expression as 3 times a quadratic, and if we divide each coefficient by 3, we'll get the quadratic that goes inside the parentheses. From here, we're ready to make our first guess. We'll start by focusing on the quadratic inside the parentheses and identify that we'll get the correct linear term if we use x minus 4 squared. Then, we'll just make one change to our initial guess, which is to put our a value in front of the perfect square. At this point, we're ready to check our guess by converting it into the standard form. So we'll start by expanding our perfect square. Then, once we've distributed the leading coefficient, we can see that our guess was pretty close to the original expression. But once again, the constant term needs to be fixed. We can fix this by adding 7 at the end of our guess. And once we do that, we've successfully converted into the vertex form. As we've done before, let's practice this new skill a bit with some examples. This first example will be pretty straightforward, but one thing to note is that when we factor out the 8, it doesn't really matter what we put for the constant term inside the parentheses. Since the linear term in the parentheses is what we use to determine our perfect square, we aren't actually using the constant from the parentheses for any of our calculations. As long as we know what the original constant was, we'll be able to find our k value without any issues. Another thing to note here is the importance of understanding the process we followed rather than just looking at the final result. If we look at our work at the end of the problem, it might seem like we pulled our answer out of thin air. But remember that we actually started with just this portion of the vertex form, and then we added on the k value later. If that's challenging for you to remember, it might be worth it to show your work in a different way. As we go through this next example, we'll start by labeling our first guess and simplifying that expression. Then, we'll write down our second guess and verify that it is indeed correct. By showing our work this way, we can see the process that we're following a bit more clearly. Our next problem is in the factored form, and we'll start off by multiplying the linear factors. Then, we'll distribute the 2 to get the standard form. At this point, we would normally factor out the leading coefficient as our first step in converting to the vertex form. But notice that we would get the same expression that we had right before we converted to the standard form. So let's just look there to determine our perfect square. From there, we'll convert our guess to the standard form, compare the constant from our guess to the constant from the actual standard form, and modify our guess to fix the constant term. Finally, we have this expression that almost looks like the vertex form, but also has a linear term outside the parentheses. Because of this extra linear term, we'll need to go all the way back to the standard form before we're able to identify the actual perfect square for this expression. Then we can complete the rest of the problem as we normally do. Now that we have a strong foundation in determining each parameter of the vertex form, let's look at some more challenging examples to extend our skills. Up to this point, we've been working with examples that were specifically chosen so that each parameter would be an integer. But what should we do if we encounter problems that don't work out so nicely? Well, our process won't technically be any different, but there will be an extra layer of complexity when we start dealing with those non-integers. So let's jump into some examples, starting with this one. Notice that this example still just has integer coefficients, and we don't even have to worry about a leading coefficient. Nevertheless, this might be our most challenging example yet, because the linear term has an odd coefficient. This means that x plus 4 squared doesn't give us a big enough linear coefficient, whereas x plus 5 squared gives us one that's too big. So, what should we do here? Well, up to this point, we've been choosing the constant for our perfect square by cutting the linear coefficient in half. So let's continue that trend here by cutting the 9 in half. This gets us x plus 4.5 squared, which simplifies to x squared plus 4.5x plus 4.5x plus 20.25. And that simplifies to x squared plus 9x plus 20.25. At this point, we take 23 and subtract 20.25 to see that we need to add 2.75 to fix the constant term. And with that, we've completed our problem. Let's do a similar example, but use fractions this time. In this case, we need to divide -5 by 2 to get the constant for our perfect square. Then, when we expand the perfect square, we get x squared minus 5 over 2x minus 5 over 2x plus 25 over 4. The linear coefficients in this expansion combine to -10 over 2, which simplifies to -5. So we did, in fact, choose the correct perfect square. Next, we need to fix our constant term, which is currently 25 over 4. If we rewrite the 2 from the desired expression as 8 over 4, and then subtract 25 over 4, we can see that we need to adjust our constant term by subtracting 17 over 4. When we eventually get this simplified, we can see that our guess matches our original expression, so we have indeed achieved the vertex form. Next, let's look at an example where the coefficients in the standard form aren't all integers. Since the leading coefficient is still 1 though, we can start by dividing the linear coefficient by 2. However, when dealing with fractions, it'll be easier to multiply by 1/2 instead of dividing by 2. This gets us 8 over 6, which reduces to 4 over 3. Then, we'll place that fraction in our perfect square and convert our guess into standard form. At this point, we need to take -2/5 minus 16 over 9, which is equivalent to this calculation. Then, we can modify our guess and simplify the resulting calculations to verify that we have the correct vertex form. Now, let's try a problem that has decimals instead of fractions. You might think that it would be easier to deal with decimals, but you'll quickly see that our decimals can get complicated quickly. And while this example does work out in the end, we do generally try to stick with fractions to avoid situations with really long decimals and to see more precise forms of numbers. At this point, it's time for us to look at some more problems with leading coefficients other than 1. And while these examples might seem much more complicated than what we've done previously, the principles are all the same. We're still factoring out the leading coefficient, identifying the proper perfect square, and calculating the constant, even when those steps involve more detailed calculations with fractions. And for our final two examples, we'll have leading coefficients that are fractions. The main thing to remember here is that dividing by a fraction is the same as multiplying by its reciprocal. So in this example, when we factored out the 2/3, we essentially multiplied each coefficient by 3/2 to find out which coefficients we should have inside the parentheses. From there, the numbers actually worked out rather nicely, which led us to this expression as our vertex form. For the next problem, however, we won't be so lucky, as you can see here. And while the numbers in this problem might seem a bit excessive, just know that if you can do a problem like this, then you're ready to convert pretty much anything into the vertex form. Regardless of what gets thrown at you, you'll know the processes to follow, the guesses to make, and the simplifications to perform as you convert into the vertex form. That concludes part 2 of this video on converting quadratic expressions into the vertex form. Hope you learned something new, and thanks for watching.